Continuing our study of basic electricity, we come now to Ohm's law, the most important law in electricity. So far we've learned that current is electrons flowing in a conductor. When a certain very large number of electrons flows per second, we say we have a current of 1 ampere, or 1 amp for short. For reasons we won't go into, this number of electrons is about 6¼ million. We've also heard that the force driving these electrons around a circuit, the electromotive force, is measured in volts. A simple cell provides an EMF of about 2 volts. Now, suppose we connect such a cell to a circuit so that a current of 1 amp flows in it. If we double the EMF by connecting 2 cells together, the current will also double to 2 amps. So current and voltage increase together. But we also know that circuit has resistance to the passage of current. If in a circuit a voltage source of 1 volt pushes a current of 1 amp through a lamp, for example, we say the lamp has a resistance of 1 ohm, after the German scientist George Ohm. We can ignore the very small resistance of the bits of wire, by the way. So in any circuit, we have 3 items: the EMF, or pressure, measured in volts, the current measured in amps, and the resistance measured in ohms. Incidentally, to save writing ohms every time, we use the Greek letter omega. Omega. So now in our circuit with 1 volt, 1 amp, and 1 ohm, if we put 2 lamps in the circuit, what do you think will happen to the resistance? Of course, it will be doubled to 2 ohms. So what will happen to current? The 1 volt EMF will now only be able to manage half an amp. Or again, suppose in the same circuit we want to push 2 amps through. What might we do? Well, we could double the voltage, and that would do it. But instead, we could put in a bulb with only half an ohm resistance, and now the 1 volt EMF can push 2 amps through the circuit. Now, all these things are very simply summed up in Ohm's law, which says that in a circuit, the EMF is equal to the current times the resistance. That is, volts equals amps times ohms. This law abbreviates to V for voltage, E is also used for voltage, equals I for intensity of current times R. V equals I times R. A simple algebra tells us that this is the same way as saying I equals V divided by R, and R equals V divided by I. So in a circuit, if we know any 2 of the factors, we can calculate the third. For example, if we know the voltage is 6 volts and the resistance is 3 ohms, we can use I equals V divided by R to tell us that the current flowing is 2 amps. An easy way to remember these 3 combinations is to remember this helpful triangle. To use it, you cover up what you want to know, voltage, say, and you know it is I times R. Or if you want to work out resistance, cover it up, and you're left with V over I. And finally, current is V over R. And always, V must be in volts, I in amps, and R in ohms. Now, volts, amps, and ohms are all right for some circuits, but we may need to talk of millions of volts, say, or tiny fractions of an amp, say a millionth of an amp. Written out in full, 1,000,000 volts is 1 followed by 6 zeros. To save writing 6 zeros, we often write 1,000,000 volts like this, when we say 10 to the 6 volts. Alternatively, we call 1,000,000 volts 1 megavolt, or 1 MV. Similarly, a million amps is 10 to the 6 amps, or 1 megamp. And a million ohms is 10 to the 6 ohms, or 1 megohm. In the same way, we refer to 1,000 volts by saying 10 cubed volts, or we use the prefix kilo, as in kilovolts, kiloamps, and kiloohms. So that's kilo and mega. When we come to small fractions of these quantities, 1,000th, say, we use the prefix milli, little m. So we have millivolts, milliamps, and milliohms. Or just as we use 10 with a little 3 for thousands, we use 10 to the minus 3 for thousandths. And finally, we often want smaller fractions still, a millionth, say, and that is called micro, and we use another Greek letter, mu, to stand for micro. So now we have microvolts, microamps, and microohms for the 1 millionth part of the unit. And again, just as we had 10 to the 6 for millions, we have 10 to the minus 6 for millionths. You will need to become very familiar with these names. Now let's go on to the next topic, which is drawing circuits. Here's a very simple circuit. The short and long line symbol stands for a single cell. The longer line is the positive terminal. If it had been a battery of cells, it would have been shown like this, with perhaps the voltage shown as well. This rectangle stands for a resistance. It might be a coil of wire, for example. You will often come across diagrams where a resistor is shown like this. This sign means exactly the same as this one. There will usually be a switch somewhere in the circuit, and it would be shown on the diagram like this for open, and like this for closed. Of course, many circuits are not driven by batteries, so we have the symbol we saw earlier for any other power source. So this diagram represents this circuit: battery, switch, resistor, and back to the power source. So now in this part of the course we have learned Ohm's law and a little about how to draw circuits. Next we will talk about circuits with several resistors in them and about how we deal with such circuits.